Okay, so we are going to show that this one is increasing. So then by induction, so you have to show the first step is true, right? So clearly, right? So this one is obvious by just looking at these two numbers, 1 and 5 over 4. You can show that actually you can say it is strictly there is no equality, so you can show strict inequality. So then clearly y1 is less than y2. So the first step is over. So now you have to assume that it is true for some k step. And so we assume yk is less than yk plus 1 for some k greater or equal to 1. Right? For some k greater or equal to 1, yk is less than yk plus 1. So you have to show that yk plus 1 is less than yk plus 2. Okay, so you want to show this. So if you want to show this, you have to start computing yk plus 2. Okay, so this is 2 times yk plus 1, right, plus 3 divided by 4. Right? So that is what you have. Right? But you want to show this one is greater than yk plus 1. Right? So that is what you want to show. So what you are going to do is to, you know that because yk plus 1 is greater than yk, this is strictly greater than 2 times yk plus 3 over 4. Because you know yk is smaller than yk plus 1. So 2 times yk plus 1 is larger than 2 times yk. So obviously 2 times yk plus 3 over 4 is smaller than 2 times yk plus 1 plus 3 over 4. But according to this formula, this one is yk plus 1. So by induction, you can claim that this sequence is monotonically increasing, right? Because y1 is less than y2. If yk is less than yk plus 1, then yk plus 1 is less than yk plus 2. So sequence is monotonically increasing. Right? So the sequence is monotonically increasing. So you prove increasing. Now what you have to do is you have to show that it is bounded above. So obviously you can see that this number somehow is less than 2, right? So you can show that it is less than 2. If in doubt, you can show that it is less than 3 as well, right? So that's not a big problem, right? So you have to show that all these numbers are smaller than a fixed value, right? So that is what you want to show. Clearly this is an increasing sequence, so this is greater than 0, right? All of them, right? So all you want to do is to show it bounded above. So you can say that it is less than 2. If you doubt whether it will be less than 2 or not, you can go for 3, you can go for 4. So all you need to do is you have to show that this is less than some fixed number. So here I am going to show that this is less than 2. Right, so next I will show yn is less than 2. Right? So you can take is 3, you can say it is 4, you can say it is 5. Any number would be fine. Just you have to make sure it is less than 2 or 3 or 4, whatever. Right? But for all n, you have to show that. So again, you should show by induction. Right? So clearly, you know the first two steps are true, right? Y1 is less than 2 and Y2 is less than 2. Right? Here, the reason why we go for Y2 is because Y1 is given. So Y2 is the next number which comes according to the formula. So just for an extra thing, we show that Y2 is less than 2, right? But that is not necessary. And this is not necessary, just for your information. I am saying you that you can see that Y2 is also less than 2, but only Y1 is less than 2 is enough, right? Assume Yk is less than 2 for some k greater or equal to 1. So Yk is less than 2 for some k greater or equal to 2. Right. So now what you have to do is you have to show that Yk plus 1 is less than 2. So Yk plus 1 is equal to 2 times Yk plus 3 over 4. Right? So that is the formula. But Yk is less than 2. So this is less than 2 times 2 plus 3 over 4. Right? So that's 2 times 2 plus 3 over 4. That is 2, 4, 7 over 4, which is clearly less than 2. Right? So that number, so you know that is less than 2. So you can say that the sequence is bounded above. Right? So here you show that the sequence is monotonically increasing. Here you show that the sequence is bounded above. So by monotone convergence theorem, right? Hence, the sequence is convergent. Right? So this is how you show the convergent of a sequence. Right? So first you show monotonicity, right? Either increasing or decreasing, and then you show that the boundedness. If it is increasing, you show bounded above. If it is decreasing, you show bounded below. Right? So this is how you show convergence. Now comes the next question. What is the limit of the sequence? If they ask you to find the limit as well. Right? So earlier cases, we don't find the limits, right? We just verify the limits. Here, in these kind of cases, you can always find the limit, right? So here I'm going to show you how to find the limit. Right? So now, if you want to find the limit, right? So so let's take L is the limit, right? So here, you know you have the formula. Yn plus 1 is equal to 2 Yn plus 3 over 4. Right? So this is the formula you have for the sequence. So what you do is you take the limit on both sides. Right? So here, limit n goes to infinity. Here also you take limit n goes to infinity. You know, if Yn goes to L, Yn plus 1 also goes to L, right? Because we already proved at the beginning, limit is unique. So there will be only one limit If L is the limit, is the limit. And so then this is L. This is 2 times yn goes to L plus 3 over 4. Right? So if you take the limit of n goes to infinity on both sides of the formula which define the sequence, then you get an equation or you get a relationship in terms of L. Right? You get L is equal to 2 times L plus 3 over 4. From this, you can find L. Right? So this gives you L is equal to 3 over 2. Right? So this gives L is equal to 3 over 2. So therefore, limit of n goes to infinity, yn is equal to 3 over 2. So this is a big problem, right? Where you show 3 different things. First, you show monotonicity, increasing. Similarly, you can show decreasing also. And then you show boundedness. Right here, you show bounded above. Similarly, you can show bounded below also. Same idea, right? By induction. And then by using the formula which define the sequence, you find the limit of the sequence as well. So here you are able to do 3 things in one place. Right? You show monotonicity, you show boundedness, therefore you show convergence, and then you show limit. Okay? So this is how you apply monotone convergence theorem to show the limit. So now what I am going to do is I am going to give you a homework on similar kind of results. Right? So I am going to break it out into pieces so that you can handle one by one. Right? Okay, so here in this example, we are going to do, I break this problem into 4 pieces. Right, so I break this into 4 pieces. You have sequence defined by xn plus 1 is equal to a minus square root of a squared minus xn. Right, so where a is a constant number and it is strictly greater than 1. Right? At the same time, x1 is a value which is a number in between 0 and a square. Right? So now what you have to show is you have to show it is a monotonically decreasing sequence which is bounded below. Right? So here, first step, they want you to show that the sequence is bounded below by 0 and above by a square. So between the sequence xn lies in between 0 and a square for all n, right? Because n is equal to 1 case is given true. So all you have to do is to show it for n is equal to k plus first case when it is true for n is equal to k case. And secondly, you show monotone decreasing, right? So xn is larger than xn plus 1, right? So when the n increases, the sequence is decreasing. And then third part, if it is decreasing and bounded below by 0, right? So by this, you can say this is decreasing, bounded below by 0. So it will have a limit. And when you take the limit, you get the limit is equal to 0, right? So then finally, you have to show that the ratio between the two successive components of the sequence, the ratio between xn plus 1 over xn, right? We defined this as a rule for convergence earlier, right? So if xn plus 1 over xn is less than 1, then we say that the sequence converges. Here they ask you to verify the other way around. When the sequence is converging, they ask you to verify xn plus 1 over xn is equal to 1 upon 2x. Right? So it is not much theory needed, but all you need is computation. So you have to do the computations to verify that this is the these four conditions hold. Right? So now I'm going to do another example or exercise which is quite interesting and little bit challenging also. Right? So that is where we are trying to show that the Euler number E exists. And so we, at the very first day of the class, we talk about numbers. So we say that there are integers, the natural numbers first, and then 0, and then we have integers, and then we have rational numbers, that is fractions, and then we have irrational numbers that are something like square root of 2, square root of 3, and then we say that there are some other numbers such as pi and e, right? Those are called transcendental numbers. And the meaning of transcendental numbers is they cannot be a root of the polynomial. So here, pi you all know, you have seen in the radius of the circle or area of the circle, sorry, in the circumference of the circle or area of the circle, you have seen the number pi. So now what we are going to do is we are going to show the existence of the Euler number, right? So I'm going to put this as an exercise, right? Right, so I'm going to show you the existence or the derivation of the Euler number E. So this is a tricky question. So what we are going to do is we are going to show that limit of 1 plus 1 upon n to the power n is equal to a number E. Right? So we are going to show these results by using a monotone convergence theorem. Right? So E is a number just lie in between 2 and 3. Right? So it is a very interesting number called as Euler number. Right? So that's what we are going to do. So solution, what I'm going to do is I'm going to define a sequence. En be the sequence that is given as 1 over 1 plus n, 1 plus 1 over n to the power n. Right? So for all natural numbers. Right. So what I'm going to do is I'm going to show that the sequence En is monotonically increasing. Right. And so I'm going to show that the sequence En is monotonically increasing. So okay. So first En is 1 plus 1 upon n to the power n. So you write the binomial expansion of that, right? So 1 plus right? So if you write the binomial expansion, NC naught, that is 1, right? 1 upon n to the power n. Right? So NC naught is 1, and NC1 is n, and NC2, and so up to NCn times 1 upon n. Right? So then you can write it down. So this is 1 plus NCn is NC1 is 1, n over n is 1 plus NC2 is n into n minus 2 over 2 factorial into n squared plus all the way up to n into n minus 1 up to 1 over n factorial into 1 upon n to the power n. So NCn is also 1, but just for a purpose, I write that is n factorial over n factorial. Right? So you have this. So if you simplify this, so you can notice that this is actually 1 plus 1 plus 1 upon 2 factorial, right? You take out 1 upon 2 factorial and divide by n, right? N squared. N times n plus 2 divided by n squared. So that is n squared minus 2n divided by n squared. So you get 1 minus 1 upon 2 upon n. So n minus 1, no? Right, so you get 1 minus 1 upon n. And then all the way up to 1 upon n factorial into 1 minus 1 upon n and 1 minus 2 upon n, so up to 1 minus n minus 1 upon n. Right, so if you divide by n, right, so you get 1 plus 1 plus 1 upon 2 factorial into that and so on. So if this is a en, then you can write similarly for en plus 1. So if you write en plus 1, this is what you get. Right, so you get n plus 1 here, right, because of this, and you can see that right, so if you write it down, right, from binomial expansion, so this is just mechanical work. I just write the final step, right, so you can work it out and see. So here, when you write the binomial expansion of en, and then you write it in a certain way that you take the factorials out and then divide by n to the power n, or n to the power 2, n to the power 3, and so on, right? And you get a formula for en. Similar formula you can write for en plus 1, right? So clearly, 1 minus 1 upon n and 1 minus 1 upon n plus 1. So if you see a relationship, right? So clearly, 1 minus 1 upon n is smaller than 1 minus 1 upon n plus 1, right? And sorry, yeah, smaller. And similarly for others also, right? So you can easily see that. And so you can see that 1 minus 1 upon n is smaller than 1 minus 1 upon n plus 1, right? So 1 minus 1 upon, sorry, 2 upon n is less than 1 minus 2 upon n plus 1. And similarly, 1 minus p upon n is less than 1 minus p upon n plus 1, right? For all p is equal to 1, 2, whatever, n minus 1. Right, so you can see these results. This is obvious, right? Because when n increases, 1 upon n is smaller than, larger than 1 upon n plus 1. So minus is other way around. So 1 minus this is this. Right? And so obviously these values are larger than these values. This one is smaller than, this one is larger compared to this. This one is larger. And in addition, you have an extra term. Right, so up to here you have larger term, and then you have one extra term, right? So clearly the terms in En plus 1 are larger than the corresponding terms in En. At the same time, En plus 1 has one extra term as well. So you can clearly say En is less than En plus 1 for all n. Okay. Right, so that's guarantees the monotone increasing. Right, so En plus 1 is less than En, so it is monotonically increasing. Right? Now we have to prove boundedness. Right? So it is strictly increasing. So now if it is increasing, you have to show the boundedness. Right? So we are going to show En is less than 3. Right? So again, I'm going to come with these terms because you know that in En these are the terms you have, right? 1 minus 1 upon n, 1 minus 2 upon n, and everything. So again, clearly 1 minus 1 upon n is less than 1. Right? So you know that. Similarly, 1 minus 2 upon n is less than 1. All the way up to 1 minus p over n is less than 1. For all p is equal to 1, 2, up to n minus 1. Right? So that is clear. So here En is 1 plus 1 and this is plus 1 over 2 factorial n plus 1, so that is less than 1, and then again the other side you have n plus 1 less than 1. So you know that En is less than 1 plus 1 plus 1 over 2 factorial plus the other one 1 over 3 factorial plus all the way up to 1 over n factorial. Right? So from this line, you know that En is 1 plus 1 plus 2 factorial over this is less than 1, and then 1 over 3 factorial, the other terms are less than 1, plus 1 over n factorial, these terms are less than 1. And so all of them are less than 1. So En is less than 1 plus 2 factorial plus 3 factorial and all the way down. But we already proved that 1 upon n factorial is less than this. And so this is less than 1 plus 1 plus 2 squared, right? Or 2, actually this is 2, right? Right, so this is less or equal to, right, so this is less or equal to 1 upon 2, 1 plus 1 plus 1 upon 2 plus 1 upon 2 squared plus 1 upon 2 to the power 3 and so all the way up to 1 upon 2 to the power n minus 1. Right, so this you can prove by induction again. I believe we must have proved it in one of the previous classes, so that's true. So then you can simplify this in this way. Just the geometric series sum. All you have to do is the geometric series sum. Okay. So the geometric series sum is this. And so this is the geometric series 1 plus 1 over 2 plus 1 over 2 square plus 1 over 2 to the power n minus 1. So this is basically equal to 1 plus 1 minus 1 over 2 to the power n over, right? 1 over 2 to the power n over 1 minus 2. 1 minus 1 over 2. So 1 minus, or you can say this completely. That is easy so that you understand the geometric series, right? So this is the sum of the geometric series 1 minus 1 over 2 to the power n over 1 minus half. So if you simplify this, this is 2 minus 2 over n. So this is 1 plus 2 into 1 minus 1 over n. Right, so if you simplify, you get it is 1 plus 2 times 1 minus 2 over n. And that number is less than 1 plus 2 times 1. Right, so this is clear. This is less than 1 times 2 times 1 because 1 minus 1 over 2 to the power n is strictly less than 1 for all n. So that is 1 plus 2 times 1. So that is 3. Right, so clearly now you have the sequence is monotonically increasing and bounded, right? So at the same time, you can clearly say that En is obviously greater than 2 because 1 plus 1 plus 1 upon 2 plus and so 1 upon 2 factorial into 1 minus 1 upon n and so on. So clearly that is strictly greater than 2, right? So at the same time here we prove that it is strictly less than 3. So it has a limit. It is monotonically increasing. It is bounded above. So it has a limit. And that limit is a number in between 2 and 3. So that is clear. So in that case, we can say that that is the Euler number E, right? So right, so Euler number is a number of a limit of the sequence 1 plus 1 upon n to the power n, and it is a number lies in between 2 and 3. Right, so that is the Euler number. Right, so this is how we show the Euler number. So we will stop here, and in the next class, what we are going to do is we are going to see, right, what do we mean by subsequence, right? So far we are talking about sequences. In the next class, we are going to talk about subsequences. That is taking a small piece of a sequence within a sequence, right? And then we are going to see the properties of that, right? So that we will see on Monday class, right? So we'll stop here and then continue on Monday.